We have seen how to use the choice of our basis we made for the 4 subspaces connected with the matrix A to get the product decomposition and the sum decomposition of a matrix. So, we had A, any real matrix m by n, and then from that we constructed the 2 square matrices, which was L A transpose A, which is an n by n matrix, M A transpose, which is an m by m matrix, and both were positive semi definite matrices. Now, using these 2 matrices, we found that the basis for the subspaces can be chosen as follows. Recall our decompositions, we had R n and the R m, 2 fundamental vector spaces. A takes n component vectors to m component vectors, A transpose takes m component vectors to n component vectors, and we had the decomposition of R n as 2 orthogonal complements of range of A transpose, which was the same as range of L, and the null space of A, which was the same as null space of L. On this side, on the M side, we had the 2 orthogonal complements consisting of the range of A, which was the same as the range of M, and the null space of A transpose, which was the same as the null space of M. These gave rise to a series or a sequence of 4 orthonormal basis sets, one for the range of A transpose, the other for the range the null space of A, and then the third one for the range of A or the range of M, and the fourth one for the null space of A transpose. And these bases we denoted them as V 1, V 2, V rho. We are assuming that the rank of A is rho and the nullity is of A is nu A. This is our standard notation, and we denoted the basis for the range of L as V 1, V 2, V rho, the basis for the null space of A as P 1, P 2, P nu A, and the orthonormal basis for the range of A as U 1, U 2, U rho, and the orthonormal basis for the null space of A transpose as psi 1, psi 2, psi nu A transpose. Now, it was the choice of the basis that was important. We chose V 1, V 2, V rho as the, so we, this was our choice as the orthonormal eigenvectors corresponding to the positive, strictly positive eigenvalues of L arranged as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda rho greater than 0. And we obtained the phi 1, phi 2, phi nu A as the orthonormal eigenvectors corresponding to the 0 eigenvalue of L. We then obtained psi 1, psi 2, psi nu A transpose as the orthonormal eigenvectors corresponding to the 0 eigenvalue of L of M. Now, it was in the choice of the U 1, U 2, U rho basis, we linked the V basis and the U basis. We chose U 1, U 2, U rho as uj is equal to 1 by Sj times Avj. We know the matrix A, we have chosen the vectors V1, V2, V rho and we construct Uj as 1 by Sj Avj, where Sj is square root of lambda j, the positive square root of this is for 1 less than equal to j less than or equal to rho, and Sj's were called the singular values of A. So, this was the choice of our basis, and we chose the basis for the range of A in a way linking it with the basis for the range of A transpose, and the linking gave us this following relation: A V j, the jth vector in the basis for the range of A transpose under the transformation A goes to the jth vector for the range of A with a scaling factor Sj. Similarly, the jth vector in the basis for range of A under the transformation A transpose goes to the jth vector in the range of A transpose with the scaling factor Sj, the scaling factor being the same in both the directions. So, this was our fundamental choice of the basis. We saw we used this to get one SVD, the singular value decomposition in the product form. What was the product form? We got A as U S A V transpose, where U was the matrix whose columns were the basis for the Rm we chose, U rho, psi 1, psi nu A transpose. These were the basis for the space Rm on the right side, and these were the orthonormal basis we chose. This is a m by m matrix, and since the columns are orthogonal, orthonormal, this becomes an orthogonal matrix, orthogonal m by m matrix. Similarly, V was chosen whose columns were the basis for the Rn space that we chose, and therefore, this is an Rn cross n matrix, and this is also an orthogonal matrix. Then the SA was essentially a diagonal block consisting of this singular values along the diagonals, and all the rest of them are 0, and of course, it is an m by n matrix. So, all the zeros are adjusted, so that we get an m by n matrix. So, thus we got the product decomposition of the matrix. We also got the sum SVD as the sum decomposition. This was a product decomposition. So, now we get the SVD in the sum form, where we decompose the matrix A as the sum of row 1 rank matrices. The decomposition was A equal to summation j equal to 1 to rho S j V j tensor U j, where V j we use the notation V j tensor U j is just the matrix U j V j transpose. So, since U j is m by 1, V j is n by 1, V j transpose is 1 by n, this is an m by n matrix, and it is of rank 1, and therefore, we have A as the sum of row 1 rank matrices. So, these were the decompositions we obtained in the last lectures using this particular choice of our basis. So, that is our important construction. The most important construction in all this is choosing these right basis for these 4 subspaces. Now, how do we use these 4 bases for analyzing our system of equation. So, the use of these 4 bases, these 4 orthonormal bases to analyze the system A x equal to B. So, what is, let us denote the system by 1. So, the problem is A is given the matrix, it is a real m by n matrix. So, for given B in R m, we want to find, that is our problem. This is given, we want to find x in R n such that A x equal to B, that is 1 is satisfied. This is the problem of the system of equation. The matrix A is R m n. For any given B which is in R m, we have to find an x in R n such that A x is equal to B. Let us see how we would use these bases for answering questions regarding such a system. Now, we start with the quantity given. The given quantity is B. We must use that given information. The given information is the matrix A and the vector B. Using this given information, we have to construct that unknown vector x in order in such a way that A x is equal to B. So, how do we do this? So, let us start with the given information. So, the given B is in R m, and for R m we had chosen the basis u 1, u 2, u rho, psi 1, psi 2, psi nu A transpose is an orthonormal basis for R m. Now, B is in R m, we have a basis for R m. Any vector in the space R m now can be expanded in terms of this orthonormal basis. So, we can expand B in terms of this orthonormal basis as B. First, let us look at the components in terms of the u vectors. So, B comma u j into u j, because we have an orthonormal basis, the component along u j direction will be precisely the inner product of B with u j plus the components along the psi directions r 1 r equal to 1 to nu A transpose B psi r psi r. We shall denote this vector by x r, we shall denote this vector by B r and this vector by B n. Now, B r belongs to the range of A transpose, because range of A, because it is a linear combination of the vectors u 1, u 2, u rho. The vectors u 1, u 2, u rho are all in the range of A. The range of A is a subspace. Any linear combinations of vectors in range of A will be again in range of A. Similarly, B n belongs to the null space of A transpose, and these are the projections. So, B r is the orthogonal projection of B onto range of A, and similarly B n is the orthogonal projection of B onto the null space of A transpose. So, it boils down to something similar. It is like this: we have the R m, in R m we have the null space of A transpose and the range of A, B is some vector and it has been orthogonally projected into this two subspaces. This projection is B r and this projection is B n. So, B has been projected orthogonally onto R A and to N A transpose, and the Pythagoras theorem tells us that the length of B squared is the same as length of B r squared plus length of B n squared. So, the first achievement that we have therefore is B has this expansion j equal to 1 to rho B u j plus summation r equal to 1 to nu a transpose B psi j psi r psi r. It's the indexing has been r. So, it should be psi r psi r. Let us call this equation as star. So, we have the expansion of B. So, we know this B, our job is to find x. Where do we want to find x? We want to find x in R n. Now, for R n, we have orthonormal basis, which is V 1, V 2, V rho, phi 1, phi 2, phi nu a. And therefore, if we are looking for a vector in R n as our solution, we are looking for our solution as a vector x in R n. So, if it is going to be living in R n, it must be a linear combination of these basis vectors. So, the x we are looking for must be a linear combination of these basis vectors. Now, therefore, hence x must be of the form x is equal to say j equal to 1 to rho alpha j v j, this takes care of the linear combination of the v's, r equal to 1 to nu a beta r phi r. So, the x that we are looking for must be of this form. So, the moment we know alpha 1, alpha 2, alpha rho, beta 1, beta 2, beta nu a, the vector x is known. So, the vector x is known the moment we know these numbers alpha 1, alpha 2, alpha rho, beta 1, beta 2, beta nu. So, our job is to find these numbers. We have to find these numbers, these scalars, in such a way that A x is equal to B. So, if x is this, what is A x? We have the representation for x, it must be of this form. Therefore, A x is of the form A x equal to A of x was j, any x that we are looking for is of this form, is a linear combination of the basis vectors. Now, if we apply A, matrix multiplication is distributive. So, we have summation j equal to 1 to rho alpha j's are scalars into A v j plus summation r equal to 1 to nu r beta r into A phi r. Now, what is this equal to? We have our choice of basis was such that A v j, the v j basis went to the u j direction with the scaling factor S j. So, A v j was S j u j. So, the first sum becomes summation j equal to 1 to rho S j V j. In the second sum, the phi 1, phi 2, phi nu a, that is all the phi r's are in the null space of A. So, A times these phi r's will be the 0 vector. So, the second term will contribute only the 0 vector, and hence we get A x equal to alpha j S j u j. So, therefore, we have B expansion. We had expanded B as B u j u j plus r equal to 1 to nu a transpose B psi j psi j. This is the first expansion we got looking at the known quantity, and now we have A x is equal to j equal to 1 to rho alpha j S j u j. Now, our problem is we have to find x such that A x equal to B. So, therefore, we have the A x, we have the B, therefore, we need summation j equal to 1 to rho alpha j S j u j must be equal to the B, which is j equal to 1 to rho B u j plus summation r equal to 1 to nu a transpose B psi r psi r. Now, we can write this as summation j equal to 1 to rho, we will take all the u j terms on one side, alpha j S j minus B u j, this whole quantity into u j. On the right hand side, we keep all the psi j terms. Now, the left hand side denotes the quantities which are linear combinations of u j. Now, the vectors u j are all in the range of A. If you look at the picture that we drew, the u 1, u 2, u rho were basis for the range of A. So, any linear combination of u 1, u 2, u rho will also be in the range of A. So, this is in the range of A because u 1, u 2, u rho is an orthonormal basis for range of A. Similarly, this is in the null space of A transpose because psi 1 psi nu A transpose is an orthonormal basis for null space of A transpose. Now, the left hand side is a vector in the range of A and the right hand side is a vector in the null space of A transpose, but the range of A and the null space of A transpose are orthogonal to each other, and therefore, the only vector common to them is the 0 vector, and hence both sides must be 0. See, we have this range of A perpendicular to the null space of A transpose. So, this equal vector which is common to both of them must only be the 0 vector, because the only vector common to orthogonal complements is the 0 vector. This implies the first, the right hand side must be equal to 0 or this should be r or must be equal to 0, and summation j equal to 1 to rho alpha j S j minus B u j, this whole thing u j must be equal to theta m, not 0, but the 0 vector. Now, the given vector B is arbitrarily chosen from R m, and therefore, this system demands, if you want to have a solution, if you want to have A x equal to B, you must have chosen B in such a way that the first sum is 0. Okay. So, let us look at the, let us call this as 1 and 2. Now, first of all, 1 tells that we can get A x equal to B only if B satisfies summation B psi j equal to theta m, or we will use our R notation, or R equal to 1 to nu A transpose. Now, psi r are orthogonal vector, they are linearly independent, and therefore, the only linear component that will linear combination that will give 0 vector is B psi r must all be equal to 0, 1 less than equal to or less than equal to 2. So, therefore, the system A x equal to B will have a solution if and only if only if B psi r is equal to 0. This means that the components of B along the null space of A transpose direction are all 0, or the projection, the orthogonal projection of B onto N A transpose is 0, and hence that is only if B belongs to the range of A, which is natural, because we want A x equal to B. So, B better be in the range of A. This fact that it belongs to range of A is stated in many ways. B must be in range of A, B must therefore be perpendicular to the null space of A transpose, and therefore, it must be perpendicular to any basis, in particular to any orthonormal basis, and therefore, in particular to the orthonormal basis that we have chosen. This we will call as the consistency condition. Consistency condition. So, various ways of stating is B must belong to range of A, that is same as various ways, one or same as B must be perpendicular orthogonal to all the vectors in null space of A transpose, which we can also state as B must be perpendicular to any basis vector in N A transpose, that is all the vectors in any basis, it must be perpendicular, or the same as the same fact is now B is perpendicular to the particular choice that we have got, B psi r equal to 0 for 1 less than or equal to. This is our particular choice, and we want this to be equal to 0. So, the consistency condition, if this is not satisfied, then we cannot get A x equal to B, because for A x equal to B, we if at all it has to be satisfied, we need both these to be satisfied. So, the first one demands that B belongs to the range of A, which is stated as B psi r is equal to 0. So, now suppose B may or may not. So, let us consider the easiest case first. Suppose B satisfies the above consistency conditions. So, let us go over what we have done. We had the known vector B. We could expand the known vector B in terms of the basis for the range of M as this expansion. Then we could expand the vector x in terms of the known basis, and we got this representation, and using that we found that A x must be of this form, and therefore, using that A x must be of this form and B is of the above form, we wanted A x equal to B, and that A x equal to B requirement tells us that we need to have these two conditions 1 and 2, and the first condition gave us the consistency criterion that B must belong to this. Suppose B satisfies this consistency condition, then out of these two statements we had, one has been taken care of. Now, we have to worry about 2. So, then 2 gives us summation j equal to 1 to rho alpha j s j minus b u j, this whole quantity into u j is the 0 vector. Now, u 1 u 2 u r u 1 u 2 u rho are orthonormal, and therefore, we have seen that any orthonormal set is linearly independent and hence linearly independent, and here is a linear combination of the linearly independent vectors 0, and therefore, the coefficients must be equal to 0 for 1 less than or equal to 0. This means that alpha j must be equal to beta. So, this says how to choose. Remember, we are trying to find x. Finding an x means we must find alpha 1, alpha 2, alpha rho and beta 1, beta 2, beta rho. Now, all the analysis says that you have to choose the alphas such that alpha j is equal to b u j by s j, and this does not say anything about beta j. Whatever beta j's you choose, they are not going to affect your solution, because when we computed the a u j, if you remember, when you calculated the a u x, the beta j's came completely disappeared because a phi was 0. So, whatever betas we choose, that is not going to affect the system, and hence the betas can be chosen in any way we want, and thus we have alphas have to be chosen as we have here. Alpha j's are beta u j s j, and beta r can be chosen arbitrarily. Therefore, the x we are looking for, the solution x must be of the form x is equal to summation j equal to 1 to rho alpha j must be equal to b u j by s j into v j plus beta r's can be chosen any way you want, beta r phi r, where beta 1, beta 2, beta nu a can be chosen arbitrarily in R. So, thus we have the solution. The moment B satisfies the consistency condition, we have the solution, and we know that any solution must be of this form. So, any solution is of this form. So, now let us therefore summarize. So, therefore, summarizing, we get when B satisfies, B belonging to R m satisfies the consistency condition B psi r equal to 0 for 1 less than or equal to r less than or equal to nu a transpose consistency condition, then A x equal to B has a solution, and any solution must be of the form x equal to summation j equal to 1 to rho b u j by s j into v j plus summation r equal to 1 to nu a beta r phi r, where the beta r's belong to r 1 less than to r less than to a can be chosen arbitrarily. So, when B satisfies the consistency condition, we have the solution, and any solution must be of this form. Now, where does the arbitrariness into the solution come? The solutions are arbitrary nature in the sense that the beta 1, beta 2, beta nu a can be chosen arbitrarily. Now, if the nu a is 0, then rho will be n, and the second part will completely disappear, and therefore, the arbitrariness will be disappearing. So, the arbitrariness is in the solution is due to the B 1, B 2, B nu. Therefore, hence, if nu a is 0, that is, if rank plus nullity is n, if nu a is 0, that means if rank is n, then there is no arbitrariness, because there are no betas there now, there is no arbitrariness, and we have unique solution given by x is equal to summation j equal to 1 to rho, where now rho is equal to n. We are taking the case rho equal to n b u j by s j into v j. This is the unique solution in the case. If the nullity of A is not equal to 0, then rho is less than n, and we have infinite number of solutions, because beta 1, beta 2, beta nu a can be chosen arbitrarily. So, in this case, when we are having rho is less than n, we have infinite number of solutions. When rho was equal to n, we have unique solution. When rho is less than n, we have infinite number of solutions. Now, all these infinite solutions are of the form x is equal to summation j equal to 1 to rho b u j by s j into v j plus summation r equal to 1 to nu a beta r phi r, because now the betas can be chosen arbitrarily. Now, if you look at this part, these are all linear combinations of the vectors v 1, v 2, v rho. The vectors v 1, v 2, v rho form an orthonormal basis for the range of A transpose, and therefore, any linear combination will also be in the range of A transpose. So, that is a vector in the range of A transpose, and the second sum is a linear combination of the vectors phi 1, phi 2, phi nu a. Phi 1, phi 2, phi nu a form an orthonormal basis for the null space of A, and therefore, any linear combination of them will belong to the null space of A. We will call this as XR and this as Xn. So, XR is summation j equal to 1 to rho b u j by s j into v j. This belongs to the range of A transpose. Xn is summation r equal to 1 to nu a beta r phi r, which belongs to the null space of A, and by Pythagoras theorem again, since the range of A transpose and the null space of it are orthogonal complements of each other, we get by the Pythagoras theorem the length of x squared is equal to the length of x r squared plus the length of x n squared. And therefore, if you look at the right hand side, we find that the length of the solution will be minimum when x n is equal to 0, that is when we choose all the betas to be zeros. Hence, the solution with the least length is obtained when x n is equal to 0, the 0 vector, that is when x beta all the beta j's, when all beta 1 equal to beta nu a equal to 0. So, this solution is called the optimal solution. This solution is called the optimal solution. It is called the optimal solution, and we will denote it by x optimal, and that is given by j equal to 1 to rho b u j by s j v j, where now rho is less than n. So, what is the conclusion? Let us again summarize. If we now summarize this whole process, we have if B satisfies the consistency conditions, these are the consistency conditions. If B satisfies these consistency conditions, then A x equal to B, the system A x equal to, of course, B is in R m. If B satisfies this consistency, A is a matrix which is in R m n, let us write all the notations in the summarization. If B satisfies this consistency condition, where the size, phi's, u's and v's are the same as we have in the figures that we have been drawing, the corresponding orthonormal basis. So, when B satisfies this consistency condition, the system has a solution. The solution 1, the solution is unique if the rank of the matrix is equal to the number of columns, and the unique solution is given by x is equal to summation j equal to 1 to rho, rho is the same as n, b u j by s j b j. If rho is less than n, then there are infinite number of solutions. There are infinite number of solutions, and they are all of the form x is equal to summation j equal to 1 to rho b u j by s j v j plus summation r equal to 1 to nu a beta r phi r. Beta r can be chosen any way we want r. And among these solutions, the solution having least length is called the optimal solution and is denoted by x optimal, and we have x optimal is equal to summation j equal to 1 to rho now less than n b u j by s j into b. In the case when rho equal to n, there is only one solution, therefore, that is also the optimal solution. If there is only one person, he is the lowest as well as the highest. So, among all the solutions, there is only one solution and therefore, he is also the optimal solution. But when rho is less than n, there is this possibility that there are an infinite number of solutions can be found. Now, among these infinite solutions, which are all of this form, this gives us the structure of all the solutions. Among all these solutions, there is a solution which has the least length, and that is called the optimal solution, and that optimal solution has this structure. So, if we know what is the consistency condition in terms of the basis that we have chosen, and we have also seen so far that if these consistency conditions are satisfied, when is the solution, we know that the solution exists and we know when the solution is unique. This is the case where the solution is unique and we know exactly how the unique solution looks like. This is the case when rho is less than n, we have infinite number of solutions and we know how all the solutions look like, and then from that we know how to generate a representative solution, namely the solution with the least length or the optimal solution. All these are obtained in the terms of the basis we have chosen. Now, if you look at the unique solution that we got, all we have done is we have taken the jth component of B and scaled it down by a factor of 1 by S j and took that as the jth component of x. So, basically therefore, as we observed, A takes the jth basis vector on R n to the jth basis vector on R m with a upward scaling factor of S j. So, when we want to find the solution, we are pulling back things. So, we are pulling back the jth component of B to the jth component of x, but now scaling down the factor, because the scaling up by A has been undone by the scaling down of S j. Similarly, even in the optimal solution case, we are looking at only that part of B which belongs to the range of A, and then we are pulling back again the components with a scaling factor. So, basically therefore, we are saying that since A has a fundamental effect of scaling up by S j while going from the range of A to the range of A transpose, we have to do the scaling down while coming back to find the solutions. So, thus we have in the case of the B satisfying the consistency condition, we have all the answers, we know when the solution is unique, we know when it is unique what is the structure of the solution, and we know when the solution is infinite, and if it is infinite number of solutions, we know the structure of all the solutions, and we also know how to choose a unique representative among these infinite solutions. He is the optimal solution. So, thus we have a complete analysis of the system A x equal to B in terms of the basis we have chosen in the case when B satisfies the consistency conditions. Now, therefore, we next look at the case when B belonging to R m does not satisfy the consistency condition. Now, what does it mean to say that B does not satisfy the consistency? What does it mean? To say that B does not satisfy consistency condition. First, let us analyze that. What it means is the following: B satisfies means B satisfies C, the consistency condition C means B belongs to range of A. We put it in many forms: B belongs to range of A, or B is orthogonal to all the vectors in the null space of A transpose, or B is orthogonal to the psi j vectors, and so on and so forth. All of them mean the same thing, that means B belongs to range of A. But if B does not satisfy C means B does not belong to range of A. So, therefore, we have the following situation: we have the R m side and we have the range of A, we have the null space of A transpose. So, the B is somewhere here falling outside the range of A. B does not belong to range of A. What does that mean? We have R n, A takes the vectors R n to R m. So, therefore, if we now look at the R n side, and if we take any vector x in R n, A x will always go and fall in the range of A. So, any vector in R n, if we calculate A x, it will be in the range of A, but since B is not in the range of A, B will not be equal to A x. So, B does not belong to the range of A means for any x belonging to R n, we cannot get A x equal to B. Therefore, B minus A x will not be equal to the 0 vector for any x in R n, because the moment B becomes equal to A x, then B belongs to the range of A. So, B does not satisfy the consistency condition means B does not belong to the range of A. B does not belong to the range of A, that can be translated into the fact that B minus A x is not equal to theta m for any x in R n. This means, since it is not 0, its length squared will not be 0, and therefore, it will be strictly 0, and this we will call as the error of, if we take x as the solution, if we had thought x A x equal to B, that is, if we had thought x as the solution of the system, we would get an error because A x is not equal to B, and that error is measured by what is the difference I am getting. If I had thought A x as the solution, I should have got B, I did not get B. So, the error is B minus A x squared, and that I will call as the square error E B x. So, E B x is called b minus a x squared, and it is called the square error of taking x as a possible solution for a x equal to b. So, now what we would like to do is, since nothing is going to go to b, we would like to get as close to b as possible. So, we would like this error to be minimum. We would like this error to be minimum. If x belongs to R n is such that this error is minimum, we will call it x L is minimum, we call it least square solution. Least square solution for A x equal to b. So, therefore, what is the notion of the least square solution? So, definition x L belong to R n is called least square solution for A x equal to b if you look at the error taking x L as the solution, that will be less than or equal to if you take any x as the solution for every x in R n. That is same as the error of taking x L as the solution will be always less than or equal to the error of taking any other x. So, our only hope is to find least square solutions when b does not satisfy the consistency condition. We shall next see how to use the basis that we have chosen to find the structure of these least square solutions.